Good morning, relativity friends. I live in an agricultural community. Uh, there's farmers all around, great people, hardworking people, the salt of the earth. But they already think I'm nuts. So one of them said, "Hey, Cap, what you been doing?" I said, "Well, I've been studying." And they said, "Well, what have you been studying?" I said, "Relativity." And they said, "Well, why would you do that?" It's actually a very good question. Why would you study relativity? Because we live in a Newtonian world that's dominated by the old Newtonian physics. And all of us are in pretty much the same gravitational the field. So, myself living at sea level compared to someone living in Nepal, there's not much difference at all. We also move very slowly, right? So, none of us are ever going to move in speeds that are comparable to the speed of light. So they're just totally the relativistic. And also, most of us will never get to go into space. I hate to burst anyone's bubble, but it's just a fact. So why would you study this field? Well, to me, a relativity, it's the most beautiful the theory I think I've ever studied. It just makes you think of things that are not in our everyday lives. So it's just a never ending surprise of things you can learn in studying this field. Here's a real world example of relativity. Okay, you know that we have GPS, the satellites orbiting the Earth, because a lot of people use GPS on their phone to find locations, blah, blah, blah. Well, on the satellite is an atomic clock, and on the ground are atomic clocks. And the way GPS works, these two things have to agree on what time it is. But because this is traveling around the Earth very quickly, enough that it kicks into the relativistic speeds, the time on this clock slows down compared to this clock. And because this clock is in a gravitational the field and this one is in a less gravitational field because it's in orbit, that makes its clock speed up. So there's two competing things. And you can use general relativity to calculate exactly what that time difference is going to be. And it turned out to be true. It really was. So you just make a correction in the software so that both of these agree because you know how high this is, you know how fast it's going. So you make those two corrections and you get a time they both agree on. So that is a real world example of relativity. Now, who would ever think of this? I mean, it's just so cool, I think. But how much math do you need to really study this? Well, it's really not as much as you think. Okay, now let's get something on the ground rules here. I'm not talking to students. Students, you have a job to do. Your job is to learn as much as you can, pass exams, get out of there, make a difference in the world. I'm talking to people like myself, to curious people, continuing education people, retired people, anybody that wants to learn new things. I think this is a great field to study. But the math of it is so intimidating that most people just open a book and go, "Are you kidding me? I don't want anything to do with this." Well, you really don't need as much as you think to study some of the parts of general relativity. The best and brightest minds have been working on general relativity for 100 years. Do I think I'm really going to make a contribution to this field? Of course not. There's no way I'm going to do that. But that doesn't stop me from learning about it and enjoying it. So, what are my goals? Well, I wanted to learn new types of math. I got an introduction to vector calculus somewhere along the path. I don't know where. Uh, and it was one of those things you say, "Well, I'll never see that again." But now here I am, all these years later, and I'm learning tensor calculus, which is the generalized form of vector of the calculus, and it is absolutely fascinating. I love this field. I don't know why. There's something about it I just really like, and I can't stop reading about it. I love it. I like to do problems. I know. The other thing I'm learning is Riemannian geometry. This is the geometry of space-time that Einstein based his theory of general relativity on. And this one is extremely complicated. I'm struggling with it, but I'm not going to stop. I enjoy it, so I'm going to keep going. And I want to just solve the Einstein field equations for some simple the systems. I'm not going to try to publish a paper. There's no way I'm going to be able to do that. So my goals are modest, and I enjoy doing this. So that's why I'm studying it. There's no other reason. Let's look at some of the equations that you would use in general relativity. You need to learn about the tensor, which is given as the dot the product of the basis of the vectors in whatever the curvilinear, the coordinate system that you're going to use. All right. You're going to learn about something called the infinitesimal line element, which, as an example, is the difference between two events in space-time, which is given as the product of the metric, the tensor, times the derivative of uh, the coordinate systems of how many dimensions you're using. So you're going to use differentials here. You're going to use the products here. So there's two types of math you're going to use. You're going to learn about something and use something called the Christoffel, the symbols, which are basically the corrections you're going to need because these basis vectors are changing in your space you're working in because it's curvilinear, the coordinates, and they change every direction you change. So this thing connects them all together. It's sometimes called the connection, the coefficients. You see it has a metric tensor in it as well. It also has the partial differentials of metric the tensors. So you need to understand how to do partial differentiation. So here's three types of math: the regular kind in calculus, the product you learn from vectors, and the partial differentials. All right, so there's some things you need. And this is the Riemann curvature, the tensor, which is a very formidable looking equation, and rightfully so. And it's also got partial differentials of these Christoffel, the symbols. So once again, there's something you would need in math. And the other thing you would need from tensor of the calculus is you're going to change this 4-index the tensor down to a 2-index tensor. So you need to know how to do the tensor contractions. Excuse me. And then you solve the the field equations. So all the stuff you've done above is for the left side of this, which has to do with the geometry, and it leaves this side, which has to do with energy and matter. So this tensor here, the stress, energy, momentum, the tensor, is a beast. I'm struggling with that. I'm trying to understand it. It takes a lot of physical insight as to what you want to put in this tensor. So that's it. That's basically all you need to study it. Excuse me. Now, if you want to know how to derive these, where they come, I mean, they're here. So someone already derived them. But if you want to take the time and effort to derive these, which is actually a lot of fun, you need a lot of tensor calculus, a really, really lot. Okay. So that is a whole different story. If you want to know where all this comes from, that is a buttload of mathematics. If you just want to use them, that's not the same thing. All right. So anyway, I thought that might help. I'll see you later.